Hello, everyone. Good afternoon. Welcome to the Kirby seminar series. Before we begin, I'd like to acknowledge the traditional custodians of the lands we gather and pay my respects to elders past and present. Today, we have two talks, so a few housekeeping announcements. If you are joining us online today, there is a Q&A button at the bottom of the screen, and press that and pose your questions. And if you are in person today, there are two microphones on either side. So we'll be taking questions after each talk. And so it's my pleasure to introduce Samaneh, who is my PhD student and who's going to talk about proteomics in dengue. Sami did a very difficult but an excellent PhD. I'm a bit biased, but both her examiners gave her A's with hardly any corrections, and she was awarded the degree last Friday. So over to you, Sami.
Good afternoon, everyone. I'm Samaneh Moallemi. Everyone calls me Sami, actually. And before starting my presentation, I would like to acknowledge the Bijigal people of Eora Nation and pay my respect to their elders, past, present. Today, I'll be presenting my PhD research on early biomarkers to predict plasma leakage in dengue infection. So let me start by putting dengue into perspective as global health emergency. Dengue has become one of the fastest spreading vector-borne diseases worldwide. In 2023 alone, there were over 6.5 million cases with more than 7,300 deaths across 80 countries. But 2024 was unprecedented. That number almost doubled to nearly 14 million cases, the highest ever recorded. This creates enormous healthcare costs and system strain, particularly during seasonal outbreaks when hospitals become overwhelmed. With 4 billion people at risk and the disease spreading into new areas, mostly due to climate change, dengue represents a massive public health challenge, especially in resource-limited settings where most cases occur. I should add that despite this burden, there is no specific antiviral therapy for dengue, and clinical care remains supportive. Although dengue vaccines exist, like Dengvaxia in restricted groups, indication is limited, and this together makes early risk prediction and triage crucial. So this brings us to the core clinical problem that motivated my research. Currently, we cannot predict which dengue patient will develop severe complications early in their illness. During outbreaks, hospitals face an impossible choice: admit everyone with suspected dengue and overwhelm the system, or discharge patients and risk missing those who will deteriorate. The reality is that about 35 to 38% of hospitalized patients actually progress to plasma leakage. I mean, from febrile to critical, as shown in this table. Plasma leakage is a hallmark of severe disease, and while the rest actually could potentially be managed as outpatients, I mean, from febrile to recover indirectly. Without predictive tools, we're stuck in this cycle of over-hospitalization while simultaneously missing opportunities for timely intervention in those truly at risk. So what exactly plasma leakage is and why we focus on plasma leakage as our primary endpoint? Plasma leakage is the defining pathophysiological event in severe dengue. It occurs when capillaries become permeable and fluid leaks from blood vessels into tissues and body cavities, usually around day 5 to 7 of illness. Here's why this was the right choice for our research. Unlike broader severity categories like dengue hemorrhagic fever or severe dengue, which are composite diagnoses with subjective elements, plasma leakage can be measured objectively through rising hematocrit or ultrasound of fluid accumulation. Critically, almost all patients who develop severe disease exhibit plasma leakage first, making it both an ideal predictor and a clinically relevant measurable endpoint. So based on what we said, our study rationale was clear. Focusing specifically on plasma leakage would be more clinically useful than predicting broad severity categories. We hypothesized that patients with dengue who develop plasma leakage exhibit distinct early alternation in the circulating proteome compared to those who don't develop plasma leakage. And that specific protein or combinations of proteins detected early in infection could serve as predictive biomarkers that can reduce the number of patients in hospitals and allow supportive care to those who need it most. So based on that, we started our research with a comprehensive systematic review and meta-analysis to understand what was already known. This paper is published. This analysis identifies several key biomarkers for existing severity categories. CRP, AST, albumin, VCAM1, and Syndecon1 were some of the proteins that we identified. However, we observed a major knowledge gap. Very few studies had specifically investigated biomarkers that plasma leakage itself, predict plasma leakage itself. This comprehensive literature analysis became the foundation for all subsequent experimental work that we had. So as I told, based on our systematic findings, we just founded the subsequent experimental work, and we employed two-pronged experimental approach, targeted and untargeted. For our targeted validation, which was published last January, we selected 34 biomarkers based on our meta-analysis findings and functional analysis, testing them using Luminex multiplex immunoassays in 220 patients from the Colombo dengue study that recruited patients from Sri Lanka. This cohort, Colombo, was ideal because patients were recruited within 96 hours of fever onset before plasma leakage occurred and followed prospectively with standardized outcome definitions. So this analysis revealed that elevated VCAM1 and IL-32 receptor SST2 are associated with increased risk of plasma leakage, while CCL11 was inversely associated with plasma leakage risk. And then we did further analysis based on the dengue history. So but why this dengue history matters? Actually, prior dengue exposure is one of the strongest risk factors for severe disease, with secondary infections having significantly higher risk of plasma leakage due to a phenomenon called antibody-dependent enhancement. And when we stratified by immune history, we found distinct biomarker profiles. CXCL11, as shown here, were protective in primary dengue, while in secondary dengue infection, VCAM1 associations were much stronger, and SAA was associated with decreased risk of plasma leakage. These patterns point to early endothelial activation and immune dysregulation preceding plasma leakage with different pathways in primary and secondary dengue infections. While our targeted validation confirmed some potential important biomarkers, we realized we were only seeing part of the picture. To truly understand the molecular mechanism driving plasma leakage and discover entirely new and novel biomarkers, we needed to cast a much wider net. This led us to our second major approach, unbiased high-throughput discovery proteomics. For discovery proteomics, we used two complementary high-throughput platforms on the same samples, LC-MS, liquid chromatography mass spec, for unbiased discovery detecting 1,358 proteins shown in blue, and SomaScan aptamer-based proteomics identifying 9,665 protein targets shown in red. Combined coverage was more than 10,000 proteins. This dual platform approach was designed to maximize proteome coverage regarding the high magnitude of plasma proteins and also enables cross-validation. After that, we conducted several different comparison and analysis, including dengue versus non-dengue and various stratification. However, for this presentation, I will focus on core finding that we had, the plasma leakage signatures, which represent our primary research question and most clinically relevant endpoint. Now moving to our discovery proteomics results. Using linear modeling with empirical based moderation, we identified 23 proteins that were differentially expressed in the same direction across both independent platforms in patients who develop plasma leakage. This cross-platform validation addresses, in some aspect actually, a critical challenge in biomarker research, which is reproducibility. Most biomarker discoveries don't replicate, It's not just underpowered studies, case mix heterogeneity, and pre-analytical variability, but also platform artifacts and analytical bias that all undermine generalizability. The fact that these 23 proteins were independently confirmed using two completely different technologies dramatically increases our confidence that we've detected real biological signals, not methodological noise. So this represents our most robust candidates for plasma leakage prediction. Some of these 23 proteins included master regulators for immune responses like STAT1 and STAT3, extracellular matrix components, stress response proteins, and metabolic regulators, showing multifunctional process leading to plasma leakage. Remarkably, 17 of these 23 proteins had never been previously linked to dengue, representing entirely new biological pathways for understanding plasma leakage pathogenesis. Those which were previously studied in dengue are shown in red. In this graph, I'm showing three independent approaches we had in my study that all led to the same groundbreaking conclusion. Our systematic review showed liver markers, ALT, CRP, albumin, were the most consistent early predictors. Our targeted validation confirmed liver involvement with SAM and ferritin, but most striking, our unbiased discovery proteomics revealed 14 out of 23 biomarkers were hepatocentric proteins. Actually, this is the biology telling us that dengue is fundamentally metabolic inflammatory disease, which is hepatocentric, and not just immune pathology, where liver is the epicenter, not a bystander. In proteomics, we use pathway and network analysis to make sense of large data sets by identifying which biological processes are enriched among our proteins. Here's one key example comparing primary versus secondary dengue. Getting back to previous figure, comparison 2 and comparison 3. Actually, clinical detection of dengue history is often self-reported due to the cost, and so this is unreliable. So it's important to identify signatures that distinguish this primary and secondary. This bar graph here shows enriched pathways with the x-axis representing the statistical significance and colors indicating a strength of enrichment. We look at both upregulated pathways, what's being activated, and downregulated pathways, what's being suppressed. The results reveal fundamentally different molecular signatures. Primary dengue, as can be seen here, shows upregulation of glycolysis, extracellular matrix interactions, and proteasome components, essentially a coordinated stress response to first-time viral exposure. Secondary dengue in this graph is shown tells us a completely different story. We see pronounced metabolic dysregulation in amino acid and lipid metabolism, intensified inflammatory signaling, and autoimmune-like features consistent with antibody-dependent enhancement. While both share metabolic adaptation signature, secondary dengue shows broader proteomic shift with inflammatory amplification and vascular destabilization pathway. This explains why secondary infections are typically more severe and why this matters clinically. We are not just dealing with one disease, we are dealing with two molecularly distinct processes that happen to share the same clinical endpoint. Looking forward, our findings provide a clear roadmap for clinical translation. The immediate next step could involve quantitative validation of these 23 proteins in independent cohorts from different countries to demonstrate generalizability across populations. We also need pediatric validation, since children have different primary to secondary infection ratios. So just to summarize, we identified 23 plus 5 robust biomarkers, plasma biomarkers, that predict plasma leakage in dengue. These proteins reveal the hepatocentric and immune regulatory signatures that differs fundamentally between primary and secondary dengue infection, offering novel insights into dengue pathogenesis. Importantly, the pathways we've identified, including endothelial dysfunction, immune dysregulation, and metabolic reprogramming, may underpin vascular complication across viral hemorrhagic diseases like Ebola, sepsis, and COVID-19, suggesting wider diagnostic applications. These positions are finding not only for dengue-specific clinical application, but as a broader framework for understanding and targeting endothelial dysfunction across medicine. And before I close, I want to express my gratitude to the incredible team that, yeah, I didn't have a picture, that made this PhD journey very much pleasant for me. Heartfelt thanks to my supervisors, wonderful supervisors. Thank you so much, Chaturaka Rodrigo. Thank you, and Andrew Lloyd, and Paul Jock, and Nicodemus Tedla. And I'm very much grateful to the Viral Immunology System Program and the Kirby Institute and the Colombo Dengue study teams, and of course, the patients in Sri Lanka whose generous contribution made this work happen. And finally, I want to thank my family, especially my parents. Thank you so much for your presence and listening to me.
Really nice presentation. Just for my sort of knowledge and others, I think, are there sort of clinical prediction models that are currently used that utilize ALT, hematocrit, and platelet count, those sorts of readily available sort of measures? I mean, this looks really interesting from a sort of pathophysiological, pathogenic sort of mechanistic sort of angle, but whether it's implementable, particularly in low sort of middle income countries, is that ultimately what you think can be translated, or how are we doing so far with the sort of currently available laboratory measures that we have in terms of clinical prediction of plasma leakage and more severe disease?
You mean considering the expenses, that is, if it's applicable in resource limited settings?
Yeah, I think, you know, to do this, to implement it in highly endemic dengue settings may be problematic. But there must be some further work that's being done looking at readily available laboratory measures to have better prediction of who's going to develop severe sort of clinical dengue.
Yes, true. Actually, these biomarkers, currently there are some studies that's showing some ALT, AST that you mentioned can be used with along with some other models to predict some sort of severity, but it wasn't general. We couldn't generalize them. And the proteins that we found, we can use them in models, along with liver enzymes, especially ALT/AST that we found in our systematic review as well, CRP as well, and use them beside them to predict plasma leakage. But regarding expenses, the combination of proteins that we found, I think not all of them can be, for example, WECAM1, for sure, it can be a little bit hard to implement in actually clinics. But regarding some other potential biomarkers that we found, I think it can be applicable if we just go through a panel of them. And it can be less expensive than, just right now, just identifying the history of dengue, primary, secondary, maybe much more expensive than what we can do, yeah, I guess. If Chaturaka can add
a little bit more to that question Greg asked, about ALT and AST and platelet count, what the standard laboratory variables that are available in the hospitals, whether they have been used in models. Yes, they have been used in models because that would be the most straightforward thing to do. But the problem is the sensitivity and specificity of those models are not. That's problem number one, high enough. And the other thing is those models have always the outcome those models have correlated with is severe dengue and dengue hemorrhagic fever with a mostly a composite diagnosis, meaning they depend on more than one criteria, some of them very subjective. So it varies from country to country how they define it. So it's not generalizable. We are not suggesting the next part, the cost. We are not suggesting that proteomics-based biomarkers, the proteomics is the discovery platform. So once they're individually validated, out of these 23, maybe about 1 or 2, if they're validated in a different country, then probably they could be scaled up production via a lateral flow test or something like that. And that would be quite useful to use in combination with other biomarkers.
I really liked the presentation. It was extremely clear. I learned a lot, so I really like when that happened. So but I don't know much about dengue. So I'm just wondering, because of I think the importance of the finding in terms of the hepatocentric sort of pathophysiology that underline some of your findings. Have you found that any demographics link into some of the biomarkers? So, for example, is there an effect of age? Are older people more likely to show a severe profile of those biomarkers, or you haven't found that's the case?
Actually, the population that we're using, the cases that we have are all adults, and the ages don't differ very much. So we don't have elderlies and we don't have children in our database.
Okay. All right, that's interesting.
Yeah.
And in terms of men and women, there was no difference either?
Regarding, no, there was no gender-based, no, there was
Okay.
no.
Well, I just think it's really important in terms of what Greg was just talking about, the implementation. If you show that all those biomarkers are independent of those effects, it's really, really critical, I think.
In the second paper that I told you that I just explained early biomarkers to predict plasma leakage, we have explained this, that gender didn't affect actually the severity regarding the biomarkers we found.
All right.
Yep.
Great work.
Thank you.
So if there are no more questions, thank you, Sami.
Thank you.